morning, everyone. In today's lecture, we are going to learn what is Laplace transform. So, what it does is it transform domain, means from time domain to frequency domain. Second, it's a convenient representation for signals and LTI systems. So LTI is linear time invariant systems. Third, we can use it for analysis and to obtain valuable insights into behavior of signals and systems, and it is usually denoted by LT. So how you find it is, if you have a signal given as x of t, then x of s will be equals to minus infinite to infinite integration of xt with e raised to the power minus st dt, where s is equals to sigma plus j omega. Or you can say it is a complex valued S is complex value, or you can say x of s is equals to, another way of representing it, Laplace of x of t, or we use this symbol for it, L of x of t. So we can say that x of t and x of s form a Laplace transform pair. So it's signal and then it's a Laplace transform. So you can say that signal and LT form a Laplace transform pair. Because we are integrating from minus infinite to infinite, so we can say this is bilateral. Unilateral is that when we are integrating it from minus infinite to 0 or 0 to infinite. So this is bilateral LT, or we can say Laplace transform. One important thing which you need for Laplace transform is region of convergence, or you can say ROC. It is region of convergence, because there might be a possibility that there are two signals, and when you find their Laplace transform will be same, but where in S plane, or we can say ROC is your region of S plane, where signal converges, or more precisely its range of values of S for which the LT Laplace transform exists. So it's basically tells where the signal will exist. So if you have two different signals which have the same Laplace transform, the only difference they will have is the region of convergence where they are defined, and it depends upon the signal you are using with it. So for example, if I take my signal as xt equals to e raised to the power minus at ut, where ut is your unit step function and a is any real quantity. Or number. So a is defined as real and ut is your unit step function or signal. So if we need to find the Laplace transform of this, then it will be x of s equals to minus infinite to infinite u of t dt. Now due to this unit step function which is defined here, a range will be provided by this unit step function. So ut is basically can say 1 for t greater than equals to 0 and 0 elsewhere. So using this we can change these limits here from, because this signal exists having an amplitude equals to 1 from 0 till infinite. So we can change it. X of s will be now equal to x of s will be equals to 0 to infinite. If I bring these two together, then it will be s plus a t dt. Now it's very easy for you to find the integration of it, but we have, because we are doing now Laplace transform, so we have to take care of the region of convergence also. Now when you will do the integration of this, so x of s will be equals to e raised to the power minus, we know the integration will be s plus a and 0 to infinite. Now you have two limits, one is infinite, another one is 0. So when you will put the upper limit, so basically putting the upper limit means that your t is equals to infinite. So when this will be equals to infinite, then e raised to the power minus s plus a infinite should be equals to 0 in order for this signal to provide you a valid answer. And this will be equals to 0 only if s plus a is greater than 0. If s plus a is not equals to 0 here, then, or you can say s plus a is negative here, so then it will become a positive, means negative and negative will become a positive, and it will be e raised to the power infinite, which will make it equals to infinite. So in order for this signal to exist, we need to have t equals to, for t equals to infinite, s plus a must be greater than 0. So this is your region of convergence. Now when you will put the upper limit with this condition, So you have x of s equals to 0, and then there will be a minus here, and then e raised to the power 0. So this minus will cancel with this minus, so it will be 1 upon s plus a. So you can say that now your x of s is equals to 1 upon s plus a, with a condition that s must be greater than minus a. So, or you can say the real part, because this is a real number, so you can say real of s is greater than minus a. So if I plot this on a plane, so if I mention it as S plane representation of my ROC. So you can say this is your sigma. Why? Because S is equals to sigma plus j omega, and this is j omega. Sometimes in some books it is written as real S, and this is written as imaginary S. That is also true. So what number we have here is minus a. So real S greater than minus a. So the region of convergence will be real S greater than minus a. So all the values which are greater than minus a are the region of convergence of it. So we'll represent it in this way. Now if we take another example, and here xt now is equals to minus this, and I need to find the Laplace transform of it. Then it will be x of s will be equals to minus, now I'm taking it directly, or if you want, then xt is ut is defined from 0 to infinite. U of minus t will be defined from 0 to minus infinite. So it will be minus infinite to 0, e raised to the power minus at, and this. So if it goes like this, then dt. So if you take the integration of it, then it will be minus, there will be a minus due to this part, so it will be minus will change to plus, and then it will be 1 upon s plus a now here, if you put the upper limit on this, then it will be e raised to the power 0, so it will give us the answer equals to 1. The problem is in the lower limit now, means when you put t equals to minus infinite. So when your t is equals to minus infinite, then e raised to the power minus s plus a, there will be a minus infinite, this. So in order for this to be equals to 0, so if this is not equals to 0, then we will not be able to find a finite answer. So in order for this to be 0, this should be equals to negative. Why? Because we must know at this point that e raised to the power minus infinite is equals to 0 and e raised to the power infinite equals to infinite. So in order to make sure that this is equals to your this part is equals to negative, we must say that s plus a must be less than equals to less than 0, then it will converge. So now for excess we have condition s plus a less than 0. So x of s will be equals to, with the condition that, or you can write it s less than minus a, or you can write it real s less than minus a. So any one of these will be used. Now if you represent it, now here one more thing which I want to highlight here is that if you see the excess of this is equals to 1 upon s plus a, and excess which we find out here also, it is also equals to s plus a. That means for both of them, both the signal e raised to the power minus at ut and minus e raised to the power minus at u of minus t, they have the same Laplace transform. The only difference is they have different region of convergence. So if I plot it on a s plane, so it's s plane of ROC, then so this is sigma, this is sigma, this is j omega. Now the point is minus a again, the only difference is now the region of convergence now is less than this. So in this way you will do the Laplace transform of these two signals. Now at this point I want you to try two more signals with a similar form. So you will have x of t equals to e raised to the power at ut, and x of t e raised to the power at u of minus t. And you will I'll solve this in my next video. So it's basically kind of homework for you, and you can give me comments on the basis of it on this. Now in the next lecture I'll find out the Laplace transform of important signals like unit impulse signal, unit step function, sine and cosine signals. Thank you.